have an equation that will tell us that if we've got an object with a particular angular velocity and a certain amplitude, after a certain time, we will be able to know its x position, its displacement. Here's an example that you might want to try working through. Didn't show up. Here we go. Oh, there's a solution. That went wrong. Right. So here's our question. We've got a moving peg, or a moving spot, is 5 meters. That's the amplitude. And the peg is moving around the center at a constant 1.5 radians per second. That's our angular velocity. Where is the spot 2.5 seconds after starting from the positive x-axis? Here we go. So try it. Okay, so let's have a look at the solution. So we use our equation. The displacement is a cos omega t. The amplitude is 5 meters at 1.5 radians per second and after 2.5 seconds. Substituting all of that together, the position will be minus 4.1 meters. And the minus is important because we've started with a positive displacement of 5 meters over here. So after that 2.5 seconds, the minus tells us it's the other side of the equilibrium position. Let's try another one. Right, the amplitude of the spot is 5 meters still. The peg is rotating at 1.5 radians per second. How long would it take the spot to travel all the way from the far right-hand side here to the far left-hand side over here? Now, often people go wrong with this one, hence this multiple choice option of I keep getting an error message on my calculator. But this is actually the easiest multiple choice question you'll ever get. See if you can spot why. Yes, it has to be E, because that's the only ones that's seconds. But let's see what the issue is. The issue is that some people might not put that we've gone from 5 meters to minus 5 meters. Let's just look at the solution. So we're interested in how long it takes to get to the far side. So if we start with an amplitude of 5 meters, we want to know how long it will take to get to a displacement of minus 5, hence the minus 5 here. Rather elaborate working out here, but that comes out at 2.09 seconds at the end. Okay, pretty straightforward, just substituting numbers into an equation. Now, what we might be interested in is how fast is something going at a particular point in its motion. So how do we get velocity if we've got a displacement? So that's what we're going to get onto next. Here we go. Right, so just looks like what we had before. We've got our displacement time graph, but now we know the displacement time graph is basically described by this equation, x equals a cos omega t. The velocity time graph, well, we've said already that the gradient of the displacement time graph at any instant is what the velocity is. So you could manually go through and work out what the velocity is at each point, or I'm imagining that most of you, not all of you, most of you might know what you do here. Generally, we would approach this by finding the first derivative of the displacement, or differentiating it. And that would give you the velocity. Let me just skip ahead a slide. Right. So the gradient of the displacement time graph can be found by differentiating the first equation. Now, if you know how to do that, you could try that now. If you don't, It doesn't matter. It's not on our specification that you have to be able to get from one of these equations to the other. And in fact, all of these equations are given to you. So we will skip the actual method as it's not required, but we can see that if we, actually I'm going to just hide some of this and we'll go through it bit by bit. If we have the displacement is a cos omega t, if we differentiate that, we get that the velocity is minus a omega sine omega t. Now that's reassuring. That's reassuring because we've already said that the velocity time graph looks like a negative sine graph, and that's what this gives us. That's a good sign. And we can always take, it's not always, we can also take this and differentiate it again, finding the second derivative of the displacement, and it gives us the acceleration. The acceleration is minus a omega squared cos omega t. Now take a moment to copy this down, but we are going to change it slightly in a minute. So this is sort of interim notes, interim working. We will update it shortly. Now, I'm sorry, but there is another equation because quite often people are interested in the maximum values that things can take. Now, the maximum displacement, we don't need an equation from that. The maximum displacement is going to be the amplitude, A. So no equation there. But for the velocity, you should be able to see that if the velocity is minus a omega sine omega t, the maximum value that can take is, well, this does rely on you knowing a little bit about trigonometry, but sine, the maximum value that can take is 1. So there is another little equation that you can have, which is the maximum velocity. Vmax is minus a omega. Basically, sine omega t equals 1. So it's worth taking that down as well. Okay, let's try a little practice example, just like we had a minute ago. Let me just move my face out of the way so you can see what's going on. Okay, so this time the question is, what is the velocity of the spot? So again, it's a shadow that's being cast on the wall. 1 second after it started at its maximum amplitude on the right at 4.8 meters, and the wheel rotates at 2 radians per second. So first question, what is its velocity? Second question, what is its position after 1 second? Work that out, please. Okay, let's have a look. So the solution, just using, so we're not using Vmax because we don't want that, we just want to know what its velocity is at a particular point. We get Vx equals minus omega a sine omega t. Substituting all of the information in, it comes out at minus 8.7 meters per second, which means it's still heading towards the negative side, away from the start position. And what's its position after 1 second? We're just going to substitute the numbers in a cos omega t. And you get minus 2 meters. Okay. So a minute ago, I said that we were going to adapt these equations. They were just interim notes. So this is what I was getting at. Except it's not, because it hasn't skipped ahead. It's this. We've got 3 equations now. I'm trying to move myself out of the way. We've got 3 equations. Ignore this one here, but I want to draw your attention to the similarities between the displacement equation and the acceleration equation. In fact, it's easier to do if I highlight this in red. So I will highlight it in red. Whoops. Okay, so the displacement is a cos omega t. Let's look at what we've got for acceleration. The acceleration is minus a, there's an a, omega squared cos omega t. It means that we can write the acceleration in a much simpler way. We can write for the acceleration that the acceleration is minus omega squared multiplied by its displacement or its position by x. And this is the one that you'll probably need to be most familiar with. It comes up quite a lot. Now, I'm going to finish this here. We're going to go on in the next video to look how we actually, if confronted with some simple harmonic motion problems, how we approach them. But I'm going to leave you with a little task to do, and it's this. I've set a pendulum up. I've displaced it by 1 meter, and its time period is 1 second, 1.5 seconds. I want to know what the angular velocity of the pendulum is, what its position will be after 5 seconds, how fast it will be going, and the rest of the stuff that's written up here. That's the task I'm leaving you with. Over to you. I will see you in the next video.